Okay, so our next speaker is Tanner Kimberly. Tanner double majors in both physics and chemistry. When he came to my office, he said, I want to do some capstone research with you. And I said, okay, what's the idea you have? He said, I want to do something that's more related to biochemistry. And I felt like that's a relief, right? If you don't really understand, just do whatever you want. So, so he's a really dedicated student. And turns out that, he really put a lot of energy and time into this. And in this coming fall, he's going to UC Davis to actually pursue an advanced degree in chemistry. All right, so let's give a warm welcome to Tanner.
Hello, everyone. Can you hear me? Thank you for that introduction, Dr. Shi. My name is Tanner Kimberly, and my capstone project research was on biomolecular imaging with scanning electron and atomic force microscopies. And I worked with Dr. Shi and also in collaboration with the chemistry department with Dr. Laris. So some background on my project. The specific biomolecules that I was interested in imaging was this protein here that we call BAF-R, and then this RNA molecule on the right, just RNA. And so specifically, this BAF-R protein is in all of our B cells, and it regulates their survival and their growth. So this is normal to have in our cells, and the B cells will regulate our immune system. However, there is a problem in people who have non-Hodgkin's lymphoma, which is cancer of your lymphocytes, where there's this overabundance of this protein in their B cells, and it's leading to too much B cell growth, and as you may know, too much cell growth can cause cancer and tumors, right? So that's not a good thing. What we want to do is be able to knock out these cancer cells via this BAF-R pathway, and it's been shown that we can actually do that using this RNA molecule here. So the RNA molecule will bind to the BAF-R protein in our cells. It gets into the cells, and then it's able to act as like a drug delivery system and kill those cancerous cells. So kind of a general schematic of what I just described is we have our B cell membrane here, and the BAF-R is on the membrane of our B cells. The RNA molecule comes in, and it's tethered to another RNA molecule that we call siRNA. And the siRNA is actually the important part in killing the cancer cell. That is the drug. The RNA molecule that it's tethered to is kind of like the pathway into this cell. And so once we get this complex into the cell, we can actually drop off the siRNA, which is the drug that will kill the cells, and then we kill the cancer cells. So this is effectively a cancer treatment for non-Hodgkin's lymphoma specifically. The main part of this schematic is here, where I'm investigating, is what is the exact structure that this RNA molecule and the protein BAF-R are adopting together. We want to probe that. So I started off by looking at this BAF-R protein first. So the way I did this to look at this microstructure, I used the scanning electron microscope, short for SEM. And then here on the left is an image of the instrument that we have in the Keck lab here on campus. And then on the right is like a schematic. It's a little messy, but I want to draw your attention just to this electron beam here. So our electron beam is generated and shot down directly on the sample here. And then whatever electrons are knocked off from our sample, they go into the detector. And that's how we're able to actually see our protein sample or whatever sample you're imaging. And the reason I chose the SEM rather than some other instrumentation is because it uses an electron beam. So an electron beam can see things much smaller than, say, visible light, like Scott mentioned earlier, because of the fact that the wavelength of electrons are so much smaller than the wavelength of visible light, so we can actually get much better resolution there. So the sample preparation procedure is a very complicated diagram here. I have a tube, and it's a solution of my protein, and then I drop a little drop onto a silicon substrate. So this is like just a flat, really smooth, shiny piece of silicon, because we don't want any I don't want to be looking at bumps in my silicon. I want to just look at my protein sample. And then, so now I have a solution on the substrate, and I just let the solution evaporate, and it leaves those protein molecules as like a solid on the surface. and now it's ready to be imaged. So one problem that I kept running into in all of these samples was that I had a lot of sodium chloride, a lot of salt in my protein solution. And I was like, this is so weird. Why do I have salt in here? Like, we bought this from a company. They said like it's just protein. And then I looked at the papers from the company, and they said, oh, we make this protein in 100 millimolar sodium chloride solution. And I was like, okay, that's why all this salt is coming up in my images, which is not good because I want to image protein and not salt, and that's very confusing in an SEM because you can do the EDX, the X-ray analysis, but it's really hard to like see what you're looking at. So I had to go ahead and like filter out all of this salt from my protein. So I used what's called like this Amicon centrifugal filter. So it has like here a little cellulose filter. And the cellulose has very small pore sizes at a 3,000 molecular weight cutoff. So it's going to filter out the salt because it's much smaller than 3,000 molecular weight. And any larger molecules, like the protein, is going to stay stuck in this little filter here. And then I can take that out and put it onto my silicon substrate and image it. So after this, here's kind of some later images after all the filtration and sample preparation. So we can actually see that the protein adopts these sort of like rods, like micro rods, which is very interesting. And this is on a 100 micron scale, so this is about like 120-ish microns long, and it's about probably 20 in diameter. And so when we kind of like see the size of this microstructure, and then we kind of do this calculation on how big is one protein molecule and how big is this microrod, we can actually kind of elucidate how many molecules we have making up the length of this rod. And when you do that calculation, it comes out to be about 17,500 protein molecules, which is still like tons of molecules making up just the length of this single rod. And that's the length, right? So there's many molecules that are making up the whole three-dimensional rod. And then I kind of zoomed into that little bottom part there. And that's what that looks like here. You can see it's on a 10 micron scale now. You see some finer structure where you see these little globular little lumps. And then I found another protein rod in this sample. So the protein is forming these like fibrous shaped rods. And now here we have a 50 micron scale. So this is about like 150-ish microns in length. And you can see like there's some directionality to this as well. So these protein molecules are forming kind of fibers along this rod. And you can see they're kind of sticking out here, sticking out on the sides. If we zoom into that little fiber there, you can see here on 20 microns, we have some more features. So it looks kind of like little hairs almost, just very small. And we do the same analysis as before to see how many protein molecules we actually have in this little fiber. Now we're down to about 3,000-ish protein molecules in that make up the length of that single fiber. So this is great data to get. We see these microstructures. We can see exactly kind of what type of structure the protein's adopting on the microscale, right? But if we want to get any more finer details, like on a molecular level, we're going to have to go to a different instrument. So I use the atomic force microscope to see even smaller than the SEM can. So the atomic force microscope works a lot differently than the SEM. So here we have like an image of the AFM in the lab. You can't see a lot what's going on. It has this laser cover so you don't shine yourself in the eyeball. And then it has like a TV monitor here that projects what's going on inside of the AFM. And so the TV monitor, it's like a top view. That's kind of like in the schematic, you're looking like down here. And so it's run by optical microscope, and you can see basically this little thing here is called a cantilever, and it kind of hovers over the surface of your sample. So all this green here is like my sample surface, and the cantilever is just hanging out above it. And you drop down the cantilever down to the surface, and it hovers over it and has this little tip. And the little tip is very small in diameter, and so it's basically hovering over the surface of your sample, and it's not using an electron beam to image, right? It's actually sensing intermolecular forces between the sample and the tip. So that's how you can actually map out this sort of topography of the surface. And we get the Z information, so we see height, and it's no longer two-dimensional like the SEM. And so we detect any changes in height in the AFM based on this laser light that's shining down on the cantilever. And if you can see here, there's like a little red dot right there on the tip of the cantilever, which is showing the laser light shining down, reflecting off and hitting this detector. And so now we see, oh, this distance is changing in the reflection of the light, so that must mean that our cantilever is hovering over the sample, and we map out the topography of the surface of the protein sample. So now we can see much smaller details. So here's my first AFM image of this protein, and we actually got to see the same little micro rod. So we took that in the SEM, and then we went over to the AFM and imaged this same rod. So on the left here is like a top view of our protein. And then we see from the darker color, that's 0 nanometers, up to all the way to about 2200 nanometers. And then we can actually project this into a 3-dimensional plot as well and see more of the curvature here, and you see that same scale just with no numbers. We can also do what's called like a horizontal line analysis. So we draw a horizontal line across this top view, and it will give us this quantitative values for how much the surface topography is actually changing. And we can see this surface is going, it's varying about by 1,000 nanometers, right? From 500 nanometers tall all the way to like 1,500 nanometers. Here's some more images. I'd like to point out this is a 20 micron scale, so 20 microns. Here we're down to 3 microns, so that's much smaller. And we have the same 3-dimensional image, and you can start to see these little domains where this is higher than this valley, and here we have another little peak and some peaks. So these different domains are indicating that we have different crystalline structures underneath them that the protein is being able to adopt. And then finally, here's another image that's also just 3 microns, and you can make out those sort of domains again. So in conclusion, when I'm using the SEM, I can actually make out that the protein is adopting some rod-like fibrous structures. And then when you take it into the AFM, you can make out that smaller, finer detail of the surface and actually how tall the surface is and how the topography is changing as well. So some future work would definitely involve taking the RNA molecule that I talked about earlier, imaging that in SEM and AFM, and then doing the reaction to make the complex to see how do we actually like visualize this structure that is causing the cell death, which is cancer treatment. So I'd like to acknowledge Dr. Shi for allowing me to work in his research group, Dr. Laris, who's in here from the chemistry department, and then the LSAMP for funding my work.
Questions for Tanner?
Why did you decide to look at that specific protein to that far?
Because I work with it in my chemistry research, so it was like sort of like another experiment that I was hoping to try to get more information out of this project. Yeah.
So when I was working on the AFM lab report for Dr. Shi, I was looking at a little bit into how the AFM can actually be used to like lengthen or detangle proteins.
Wow. I didn't know that.
All right.
That's really cool. Great.
Question.
Yes.
Comment on the dual degree and what you think physics allows you to add to chemistry.
I think they're such good complements, and I came in just as chemistry, but then I took physics, like intro physics, and I really liked it, and I've seen so many like connections between physics and chemistry, and we talk a lot about the same things all the time, just like different ways, and it's really weird and interesting. But so I really like to like have both perspectives, and in my PhD I hope to do physical chemistry, so like further that kind of more.
Fantastic. Let's thank